Hello, geometry students. Today we're going to be doing the review for Unit 3. So go ahead and open your Unit 3 workbook, and we're going to go ahead and just go to the end. We're going to work on the review. Hopefully you've already done the rest of the unit and watched the video where I go over the rest of the packet. If you haven't done that yet, go ahead and do that first. Now, everything that I write in the review, everything that I write here, write down, you should write down, okay? And that'll help you very much on the test. Everything on the review is on the test, so make sure you know everything pretty well, okay? Well, that being said, let's go ahead and get started. Share my screen here, and let's take a look. Okay, so if you're on the review, you should be on page 29. That's the start of the review. Now, it first goes over a few definitions. So, dilation is a similarity transformation where a figure is enlarged or reduced using a scale factor greater than 0 without altering the center. Okay, so I want you to go ahead and write that down. I'm writing these down for you because, well, they don't say them quite like this in the unit. But on the test, they definitely do say them like this. So you want to know these definitions this way so that you know them for the test. For number 2, define center of dilation. Center of dilation is a fixed point that a figure is enlarged or reduced with respect to. Scale factor, a number used as a multiplier in scaling. Now feel free to pause the video if you need to write this down. Write these down. And number 4, enlargement or reduction. An enlargement is a dilation where n is greater than 1. A reduction is a dilation where n is between 0 and 1. So basically, n is the scale factor. So basically, they're saying for enlargement, the scale factor is greater than 1. For reduction, the scale factor is between 0 and 1. So like 1/2 or something. Okay. Let me erase this. For this one, number 5, it says, is this an enlargement or a reduction, basically? Justify your answer by finding the scale factor n of the dilation and using it to defend your answer. So first, let's look at the pre-image. So the pre-image is the triangle we start with. That's this one here. So this is the starting triangle, and then the triangle you end up with is the enlargement. So the enlargement is this triangle here, or the dilation, I should say. I gave away the answer. So the dilation is this triangle here. So you could see that the image is much larger, right? The new one is much larger. So that means that it is an enlargement. Okay. So when the image, the new one with the primes, when that one's bigger, that's an enlargement. So this is an enlargement. Now it also asks us to find the scale factor. So the way we find our scale factor, n, we look at the size, the length from the image, the new one, divided by the length, the corresponding length from the pre-image. So in our case, what's the length for this right here from the image? So from B prime to A prime, what's that length there? So that length would actually be 16 plus 4 more. You see that? So because this length here to B prime to B is 16, and then B to A prime is 4. You see that? So 16 plus 4, that total distance for the image is 20. For the pre-image, it's just for the small triangle, so that's 4. This gives us the scale factor of 5. So in this case, n equals 5, which tells us for sure that it's an enlargement, because remember, an enlargement has a scale factor that's greater than 1. Here our scale factor is 5, so we know that it's an enlargement. Number 6, what are the coordinates of the vertices of D2 triangle BAC graph the image of triangle BAC. So when it has that D, that means dilation. And then this 2 down here means it's dilating by a scale factor of 2. So the scale factor is 2 in this case. Whatever number's here, that's the scale factor. So if we look at the coordinates for A, it's currently at 1, 2. So A prime, since our scale factor is 2, we're going to multiply by a scale factor of 2. So multiply each coordinate by 2. So that's going to be 2, 4. And multiply each of these by the scale factor. In this case, my scale factor is 2. So that means A prime will be at 2, 4. 2, 4. That's A prime. B is at -3, 0. So B prime, if I'm using that same scale factor, would be at -6, 0. And C is currently at 1, -2. So C prime would be at 2, -4. 2, -4. That's where C prime lives. Connect these 3 points to create the image. Now your image should look like the pre-image, just larger, okay? All the angles should be conserved. It's just a larger version of what we had before. Number 7, a pair of reading glasses shows you an image of an object that is 3.1 times the object's actual size. So this tells you the scale factor. In our case, the magnification factor or the scale factor is 3.1. So the scale factor of the enlargement is 3.1. The photo shows the glasses magnifying the Constitution by a scale factor of 3.1. So I basically just told you 3 times in a row that the scale factor is 3.1. If the average text size from the magnified was magnified at being at a height of 0.8 inches, how big must the original text size be? So this is similar to the one we did with the ants in the packet. So basically you would take the magnified image divided by the size of the original image. So we don't know the size of the original. That's what it's asking. How big is the actual, the original? The second fraction that we're going to make in our proportion, the scale factor goes on top over the original factor, which is just 1. So the scale factor, basically just your eyes, has a scale factor of 1. To solve for x, we cross multiply. So x times 3.1, that's 3.1x equals 0.8 times 1 is 0.8. To solve for x, we divide both sides by 3.1. This will give us the size of the original text. So I'm going to do, on my calculator, 0.8 divided by 3.1. That gives me that the original text was 0.258. We're going to round to 3 decimal places because it says so near 1,000. That's 3 decimal places. So in our case, the original text is 0.258 inches. The original should be smaller, right? Because remember, it's magnified. So the original text should be smaller than the magnified text. For number 8, define similar. This is the definition that they give you on the answer key. It's also what you can expect on the test. But this is not really a definition for similar. It's a definition for similar figures. But that's okay. Let's just go with this. And it still gets across the same idea. 2 figures are similar if and only if there's a similarity transformation that maps one onto the other. Okay. Triangle ABC has vertices in these locations. Graph the image of triangle ABC when you apply the composition D2, so a dilation with scale factor 2, composition with reflection across the y-axis. Now, if you remember from unit 1, we actually go from right to left. So we're actually going to do this right composition first. We're going to reflect across the y-axis. So first, we're going to reflect across the y-axis. So if A, look at A. A is 1 away from that reflection line. So A prime will be 1 away from the reflection line. B is 3 away from the reflection line. So when you reflect it, it'll be the same distance from the reflection line, 3 away. C is also 3 away from the reflection line. So the image, when you reflect, will also be 3 away. Connect these points to create the image. Okay, so now we have our 3 points here, but now we want to dilate by a factor of 2. So if we look at like where they're at now, A prime is at -1, 1. So where would A double prime be? So now we're going to dilate by a factor of 2. So -1, 1, you multiply each of those coordinate points by the scale factor. So we're going to multiply each of these by 2. So that's going to be at -2, 2. -2, 2. So this would be A. Maybe I should use a different color because it's getting kind of all over the place here. So let me go ahead and use this orange. This would be A double prime. So A prime prime is at -2, 2. What about B? Well, B prime, the original B, or I guess not the original, but this B prime is at -3, 2. So where would B prime prime be? Well, you multiply each of these coordinates by the scale factor, so that's going to be at -6, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. This is where B prime prime is. Lastly, C prime is currently at -3, -1. So C prime prime, we're going to dilate by a factor of 2. So it's going to be at -6, -2. -6, -2. Connect the 3 coordinates to create the image. And that's your final triangle there. Okay. Number 10. What is a composition of rigid motions and dilation that maps triangle PZY onto RST? So we're starting with triangle PZY, and we want to end up getting triangle RST. So you might notice, first that, okay, well, this one's definitely bigger. So we're going to have to make it smaller. So that's going to be a reduction. And also it's over here. So when it's over here, we might want to rotate it 180 degrees to get over here. Okay. Okay, so that's what we're going to do. So we're going to first say it's a rotation. So that's a lowercase r, 180 degrees. So since it's on the opposite side, it's going to be 180 degrees. Around, and we'll say O, that's the origin, 0, 0. And then, so remember, we go right to left. So, and then, well, when we do that, let's go ahead and do that rotation and see what it looks like. So P would be here. And then 1, 2, 3, 4. So it looks something like this here. Okay. Now, how do we go from this orange triangle to this triangle here? I'm actually going to switch back to blue. Well, you might notice that like this distance here is 4, but this distance is only 2. So it's half as much. So that tells us our scale factor is going to be 1/2. So we're going to dilate with a scale factor of 1/2. And then we would say triangle PZY. So you do these two things to triangle PZY, and that'll give you triangle RST. Number 11. Is there a similarity transformation that maps QWE, so this triangle, to triangle TYU? If so, identify the similarity transformation and write a similarity transformation. If not, explain. Okay. So here we know that these two triangles are similar. How do we know these two triangles are similar? Well, the two angles from this triangle match two angles from this triangle. So we know that these two triangles must be similar. Hopefully you remember that. We talked about some of the triangle similarity postulates or theorems. If two angles from one triangle match two angles from another triangle, then we could say for sure that these two triangles are similar by angle-angle similarity. Hopefully that sounds familiar. It's definitely covered earlier in this unit. So we could say angle Q is congruent to angle T, and angle W is congruent to angle Y. Therefore, triangle QWE must be similar to triangle TYU. Should be a triangle here. By angle-angle similarity. Okay, good enough. Do the two logos for the Steps Moving Company below appear to be similar? Explain. So remember, two things are similar, basically, if they are the same shape, but not necessarily the same size. So as long as they're the same general shape, they don't have to be the same size. They just have to have the same like proportional size. So like, for example, this step, the ratio between this step to this should be the same as the ratio between this to this, okay? And if that's true, then we know that these two shapes are similar. Also, all the angles need to match, but they appear to. So we don't know for sure because they don't give us any numbers, but these two shapes appear to be similar. They appear to be the same shape, but not necessarily the same size, okay? So with that, I want you just to try to explain that here, okay? Just like how I did. So these two shapes appear to be proportional in size and also have the same angles. Therefore, they appear to be similar shapes. For 13, 14, and 15, you could find the answers to these on pages 10 and 11 of this packet. So just go to page 10 and you should find the angle-angle postulate, similarity postulate, the side-angle-side similarity postulate, and on page 11, the side-side-side similarity theorem. So just go to those pages and copy the definitions down. Now keep in mind that you need to know these definitions because they're going to come up later in this review, but also on the test. Okay, number 16. Are the two triangles similar? How do you know? Well, we could see we got two triangles. We got RWS, and then we have triangle VBS. Now, if you notice, they have one matching angle kind of given to us. That's angle R and V. These two angles are congruent. You see how they have the same measure? So we can say for sure angle R is congruent to angle V, okay? And there's also another pair of congruent angles in this picture. Now, hopefully you recall, and I talked about it earlier in this unit, that when two lines cross, you end up with congruent angles opposite from each other. Remember, that's vertical angles. So in this picture, we can say for sure that this angle and this angle are congruent. So how would I name these angles? Well, you might be tempted to just say angle S and angle S, but these are two different angles. And if I just say angle S, is it really clear which angle I'm talking about? Well, I could even be talking about the angle over on top or on bottom. Angle S, there's 4 potential angle S's, right? So if I just say angle S, that doesn't really tell me. Well, instead, I could say angle WSR, and then it's clear I'm talking about this one, right? WSR. So angle WSR is congruent to angle, how would I name this other one? How about BSV? BSV. So these two angles are congruent by, or what property tells us those are congruent? Remember, vertical angles. By vertical angles. Okay. I sometimes abbreviate the word angles by just drawing an angle. So now we have these two triangles. They have two pairs of congruent angles, right? Angle R and V are congruent, and then angles WSR and BSV are also congruent. So two angles from one triangle are congruent to two angles from another triangle. Then we could say definitely triangle WSR is similar to triangle BSV. And what property allows us to say that? When two angles match another two angles? By, these two are similar by the angle-angle similarity postulate. Okay. Okay. So if two angles from one triangle match two angles from another triangle, we could say for sure those two triangles are similar because of the angle-angle similarity postulate. What about these two triangles? Are they similar to each other? So notice they don't give us any angles, so we can't use angle-angle, and we can't use side-angle-side because they don't give us any angles. So that means if they're similar, we have to be able to show by side, 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 which makes sense because they give us all the side lengths. So the way you check side, side, side is all the sides from one triangle need to be proportional to all the sides from another triangle. And then if that's true, then the triangles are similar. So the easiest way to see how to set this up is just do the smallest side with the smallest side. So the smallest side from this one, 3, is that side, right? ST. And that corresponds with the 9 from here because that's the smallest side here, right? So 3 to 9, which reduces down to 1/3. Now let's use the second smallest, so 4 here, TU, and that corresponds with the 12 here, the second smallest from that triangle. This also equals 1/3. Lastly, the 5 corresponds with 15, which also reduces down to 1/3. So since they all reduce down to the same fraction, then we could say the sides are proportional. So we could say for sure, triangle SUT is similar to triangle XWV by what? By side similarity. Okay. So anytime you're trying to show two triangles are similar, you're going to be either using angle or side angle side, or in this case, side side. All right, you're going to be using one of those three. In this case, it's side similarity. Now, this one looks very complicated, number 18, but I want you to just keep in mind that all you have to do is tell me which of those three properties you're using. Are you going to be using angle, or side angle side, or side side? And that's what's going to go down here. So they give you a bunch of information, but you could see from the picture we have these little tick marks, which means those are congruent to each other. These tick marks here means that JK is congruent to LK, right? And then we also have this swoosh marker, right, at angle J and angle F. So that tells us that those two angles are congruent. Now, if you look at these statements over here, they also give you that J and L are also congruent, right? So we know J and L are congruent. So that means if J gets a single swoosh, we could put a single swoosh right here on L. So that means that those are congruent, right? And it also says that H and J are congruent, right? So H and J, so H can also get a swoosh. So notice now, two angles from this triangle match two angles from the other triangle. Okay, then for sure we can say that the two triangles are similar, right? That's what we're saying. Two triangles are similar because of what property? Well, two angles from one match two angles from the other. That's the angle similarity postulate. Okay. Okay. And number 19, we want to find the length of x. Now, the way we do that is we use the fact that these two triangles are similar to each other. So if the two triangles are similar, we know the sides are proportional. So for example, we could say x over 20, x and 20 equals, now what corresponds to the x over here? So x is right here. What corresponds to the x over here? Well, that would be the 5. What corresponds to the 20? Well, the 8. We can use that proportion to help us solve for x. We just cross multiply and divide. So 8 times x is 8x. 5 times 20 is 100. Divide both sides by 8 to get x by itself. That gives you that x equals, I think it's 12.5. Yeah. So that means that the value of x, meaning the length here, is 12.5. Now, how do we know these two triangles are similar? Well, two angles from this triangle match two angles from this triangle. So you could say angle similarity, right? Because it asks which postulate or theorem tells you that they're similar, right? You could have also used side angle side here as well, right? Side angle side, right? But, well, I guess you can't use side angle side because we don't know the side, but angle, that works. Okay. For geometric mean, I want you to go ahead and go to page 17. And the one thing I want to emphasize is when you're writing the definition, just make sure that when you write it, and you write the proportion, make sure you write that and showing that the x is opposite from itself. So when you're doing geometric mean, you're setting up a proportion, but x has to be opposite from itself. That's key. But go to page 17, you'll find the rest of the definition. Number 21, what similarity statement can you write relating the three triangles in the diagram? So in this picture, we have three triangles. We have the largest triangle, triangle ABC. Maybe I'll draw it to the side here, ABC. Okay, drawing a little bit smaller, but it's broken away from everything else, with C being a right angle. Then there are two other triangles, right? You see how this splits it off into two other triangles? So we have triangle ADC. Maybe I'll draw it over here. And in this case, angle D is the right angle. See that? And then we have this small triangle. Draw it over here. Where, again, angle D is the right angle. So DBC. Okay, so three triangles in total. Now, when we write our similarity statement, we want to make sure that we're correctly corresponding the correct angles to each other. So if I start with this big triangle, let's just say triangle ABC is similar to, now if I look at A is the smallest angle here, right? So I'm going to do a single swoosh there. And B is like the medium angle. We'll do a double swoosh here. And C is the right angle. So I wrote it in this way, ABC. Now, if you put CBA, that's fine. Just make sure you correctly put all the other ones in the correct way too. So if I look at that, well, the smallest angle, I put a single swoosh. So on this one, the smallest angle here should get a single swoosh. That's angle A again, which makes sense because it's the same angle A, really. Right? They both come from here. And angle C is the medium angle, and angle D is the right angle. So the medium angle gets a double swoosh, right? Just like over here. So when I'm writing the similarity here, you see how here I wrote the smallest angle first, small. Then I wrote the medium angle. And then I wrote the 90-degree angle, right? Angle C. So I want to do that in that same order over here. So I do the small first, A, then the medium, C, and then the 90, D. Lastly, the small triangle, same idea. The smallest angle gets a single swoosh, and the medium angle gets a double. Notice B gets a double here, same as it did over here, right? So that'd be triangle. And again, I'm writing the small, medium, 90. That's how I wrote it. So the small, then the medium, then the right angle, the 90. Okay. If you wrote this in a different order, make sure you write these ones in the order that corresponds correctly. Now for number 22, we want to find the geometric mean of 5 and 15. So as I showed you up here, when we're doing geometric mean, you make sure that we're writing a proportion where x is opposite from itself. Okay. Then the other two lengths that they give you, or the things we're finding the geometric mean for, they go opposite from each other here. So from here, to solve this, we would cross multiply. So we want to do x times x, well, that gives me x squared equals, and then 5 times 15, that's 75. To get x by itself, we square root both sides. So that'll give me x by itself. And then over here, the square root of 75, I can simplify that square root. And the way we do that is with a factor tree. I'm going to go ahead and do it to the side here. So if I'm doing 75 and I want to break this down, well, I already know that 5 times 15 multiplies, give me 75. The 5 doesn't break down anymore. It's prime. So I'm going to uncircle it. The 15 does break down to 3 times 5. 3 and 5 are both prime, so I'm going to encircle those. So I could rewrite the square root of 75 as the square root of 3 times 5 times 5. Notice those should just still multiply back to 75 if you multiply these back together. Now, when you're simplifying a square root, you look for doubles. So here we have a double 5. So that's going to come outside the square root. So that's 5. And you're left with the square root of whatever's left inside, in this case, 3. So this is just the simplified radical of square root of 75. Now you can always check your answer, because if you multiply this in the calculator, 5 times square root of 3, you should get the same thing as if you did the square root of 75 in the calculator. They should match when you plug them in the calculator, because they should be equal. Let's take a look at number 23 here. And generally here, we're going to be using the geometric mean as well. The thing you want to look at, and the way I kind of think of it, is whatever, when I'm, let's say, finding x first, I want to use the geometric mean. And I might notice that x is shared between two of the triangles. See how x is part of the largest triangle? See how x is a side length of the largest triangle? But x is also a side length of the smallest triangle. You see that? So when I'm finding that geometric mean, whichever length is shared, that's what goes opposite from itself. So in this case, x is shared by two triangles. It's going to go opposite from itself. Now, when I'm looking at that big triangle again, what is the other side length they give you for that right triangle? For the big one? Well, they give you this length here, right? The hypotenuse of this. And what's that length there? Well, the length is 10 plus 3. So this length here is 13. Now, when I look at the small triangle, what other side length did they give you? Well, they give you that this is 3. So when we're finding now we find geometric mean between 13 and 3. So cross multiply, that's x squared, equals 13 times 3, that's 39. You square root both sides to get x by itself. That gives you that x equals the square root of 39. Now we can try to simplify that, maybe to the side, 39. But this one doesn't simplify like the other one did, like 75 did. This one doesn't simplify because when we break this down, 3 and 13, these are both prime, so they don't break down anymore. And you won't have any doubles here, so it won't simplify. The 75 did have double 5, and so that's why it simplified, but this one won't have any prime doubles. So we'll leave it just like that. Now for the y here, y is also part of two triangles. You see y is part of this medium triangle. See that? Y is one of the side lengths for the medium triangle. So when we set up for our geometric mean, when we set up our proportion here, y will go opposite from itself because it's shared between two triangles. It's on the medium, but it's also one of the side lengths for the small. See that? Y is one of the side lengths for the small triangle. So whatever thing is shared, in this case y, will go opposite from itself. Now when I'm looking at the medium triangle, what other side length did they give you for the medium triangle? Well, they give you this length, don't they? Not all the way down, not past here, but just to here for the medium part, right? So that's 10. For the small triangle, what other side length do they give you? Well, this one here, 3. Cross multiply. Y times y is y squared. 10 times 3 is 30. To simplify to get rid of the squared here, you're going to square root both sides. That'll give you y equals the square root of 30. We can see if it breaks down by doing a factor tree, seeing if there's any double prime factors. So we would say 3 times 10. 3 is prime, it doesn't break down. 10 does break down. 2 times 5. However, there won't be, see how there's no double prime? No prime gets doubled here, right? So this one won't simplify either. Number 24 is very similar to what we just did. Here we're looking for x, right here. This x is shared between two triangles. It's shared, it's part of this triangle here, but it's also part of this triangle here. So it's part of the small and the medium triangles here. So since x is being shared, the way we find it is we set up a proportion, a geometric mean proportion, where x is opposite from itself. When I look at the small triangle, the other side length they give you is 8. And when I look at the medium triangle, the other side length they give you is 10. Now we want to find x using the geometric mean, cross multiply. X times x, x squared. 8 times 10 is 80. To get rid of the squared, you square root both sides. So that gives you x by itself. Over here, the square root of 80, well, this one actually is going to simplify. So let's go ahead and look at our factor tree. So when we do 80, we could say, okay, well, that's 10 times 8. Now, I use 10 times 8, but if you did like something different, right? If you did 4 times 20 or something like that, as long as it equals back to 80. All right, and you just continue breaking it down, you should get the correct prime factors. 10 does break down to 2 times 5. Okay, these are both prime. They don't break down any farther. 8 does break down as well. 2 times 4. 2 is prime. 4 is not prime. 4 breaks down even more to 2 times 2. So the square root of 80 is the same as the square root of, and look how many 2's we have. 1, 2, 3, 4 of them. 2 times 2 times 2 times 2 times, and then we also have a 5 here. Now, when you simplify a square root, you're looking for doubles. So in this case, we have a double 2 here and another double 2 here. For every double that comes out, if it's double inside, it comes out as a single outside. So that's going to be 2. This comes out, right? And then another 2 that comes out. What's left inside is a 5, right? 5 didn't have anyone to pair with, so it stays inside. 2 times 2 is 4. So 4 square root of 5. And again, you could always double check with your calculator. If you plug in 4 square root of 5 in your calculator, it should equal the square root of 80 when you plug that in the calculator. Okay, because these are equal. They're just simple. This is just a simplified version of that. For these 3 definitions, side splitter theorem and corollary of the side splitter theorem, those could both be found on page 21 of this workbook. And triangle angle bisector theorem can be found on page 22. So go ahead and pause the video, go to those pages and copy the definitions down right here. Number 28. What is the value of x in the diagram below? So this is demonstrating the side splitter theorem here. This is the side splitter theorem basically being demonstrated. But basically what it shows is that I could use a proportion to help me find x. So if I look at this side, 10 is to x plus 1. So I'm looking at the left side here. 10 is to x plus 1 as 8 is to x. Now we want to solve for x. So what we're going to do is cross multiply. So 10 times x is 10x. equals, then 8 times x plus 1. Okay. The first thing I would probably do is distribute this 8. So the 8 multiplies with both of these in the parentheses, 8 times x and 8 times 1. So that'll give me 8x plus 8. And over here, the 10x hasn't changed, so 10x still. I could subtract 8x from both sides of this equation. So that's 2x equals, and on this side we just have 8. To get x by itself, we divide by 2. And that gives me that x equals 4. So you should get x equals 4 in this case. Number 29. Number 29, a lot of people get stuck on a little bit because they give you more information than you need. But if we look at x is to 8 as 6 is to 4.8. So notice I'm comparing x with 8, 6 with 4.8. Here this 6.4 is not needed, but it makes, so this is unnecessary information. But we could do the problem perfectly fine without it. If they gave you this, then if they gave you this length, then you could use it, right? But since they don't give you that length sitting across, then we won't be able to use it. Anyway, so x times 4.8 is 4.8x. The main thing here is if you could set up that proportion, if you could set up the proportion correctly, then you should be able to do the problem no problem. Okay, 8 times 6 is 48. Divide both sides by 4.8 to get x by itself. And that'll give you that x equals 10. So that tells you the value here is 10. Okay. Last one. Here, again, if you could set up the proportion correctly, then this problem is really easy. So here, 11 is to 13 as 21 is to x. Right. This is to this as this is to this. Cross multiply. 11 times x is 11x. 13 times 21, 273. To get x by itself, we go ahead and divide both sides by 11. And that gives me that x equals, it says round to the nearest hundredth, so that's 2 decimal places. Divided by 11, 24.82. 24.82. So make sure you put that in your calculator and you see how I got this. Again, rounding to the second decimal place gives you a 2 there. Okay. Well, that's it. I hope the review made sense. I hope you're able to get through it without too much of a struggle. If you understood everything there, then the test should be relatively easy. But I would just say make sure you have those definitions down. And make sure that you're able to set up those proportions correctly for those last few. All right. Well, with that being said, good luck on the test, and I'll see you guys next time.